Greetings everyone and welcome back to another video of Inquisitive Thinking. I hope all of you are doing well. This is part 3 of Understanding Trigon series in which we are introducing the concept of trigonometry. Can you imagine young people nowadays making a study of trigonometry just for the fun of it? Well, I did. Said Clyde William Tombaugh, an American astronomer who is associated with the discovery of planet Pluto. The word trigonometry is derived from two Greek words, trigonon and metron, which roughly translates to three-cornered and to measure respectively. Trigonometry studies the relationship between angles and side lengths of a triangle. Now, trigonometry itself is of many types. First is plane trigonometry, which deals in the study of relationship between angles and side lengths of a plane triangle. Analytical trigonometry combines the use of coordinate geometry that examines trigonometric identities in terms of their position in Cartesian, that is xy plane. And spherical trigonometry, which deals with the study of trigonometric ratios and identities of spherical triangles in which sum of all three angles is more than 180 degrees. This type of trigonometry is widely used in the fields like astronomy, navigation, geodesy, and many more. Out of all these types of trigonometry, we will currently focus on plane trigonometry, in which we'll study a plane triangle. A plane triangle is a triangle which is drawn on a flat 2D plane. To be precise, we will look at those plane triangles in which one angle is 90 degrees, which are right angle triangles. You must be thinking why? The reason is in the later section of the video. Here is a small piece of information before we start. Any triangle can be shown either as a combination of two right angle triangles or as a difference of two right angle triangles. For example, this triangle ABC is an acute angle triangle. Now, if I draw an altitude AD from point A to point D on side BC, this triangle is now divided into two right triangles. So, triangle ABC can be written as the sum of two right triangles, triangle ABD and triangle ACD. In triangle PQR, which is an obtuse angle triangle, if we do something like this, now we can represent triangle PQR as a difference of two right triangles, which are PSR and PSQ. Now let's look at a historical anecdote about one of the greatest mathematicians, Thales of Miletus, who was born around 626 or 623 BCE and lived till 548 to 545 BCE. And it goes like this. Once Thales was in Egypt, where he asked one of the priests about the height of Great Pyramid of Giza, to which the priest refused to answer. So he went on to find the height of the pyramid on his own. Now, which method exactly did he use is unknown, but it's mainly believed that he had used the property of similar triangles. Now, let's look at the supposed method he might have used to find the height of the pyramid to an almost correct value. Consider this a pictorial representation of a particular time during the day. Here is our sun, here's the sky, and here's the ground beneath. He had used the principle that at any particular time during the day, rays from the sun are essentially parallel to each other. Consider this to be the Great Pyramid of Giza, whose height to Thales was then unknown. The pyramid will cast its own shadow on the ground. Thales had then fixed a stick of known height, which will cast its own shadow on the ground. We can assume that the outlines of the pyramid will form a plane triangle. We can also assume an imaginary vertical pole from the base of the triangle to the top, whose height is equal to the height of the pyramid. For our geometric convenience, let's name these points. So here, SQ is the shadow of the pole PQ, which is made up of SR, the original shadow of the pyramid, and RQ, which is the imaginary part of the shadow of the imaginary pole PQ. You can see that RQ is equal to half of the base RT. We know AC and PS are parallel to each other since these represent the rays of sun. So angle ACB and angle PSQ are equal. Also, angle ABC and angle PQS are right angles. And here SQ is equal to SR plus RQ. So triangle ACB and triangle PSQ are similar to each other by AA rule of similarity. We also know that for similar triangles, ratio of corresponding sides are equal. So we have written PQ upon AB equals QS upon BC. And out of these four sides, these three sides are of known length. So from this equation, one can easily evaluate the value of PQ. Another method which is also believed that he had used was that he might have waited for a particular time of the day such that his shadow would become equal to his height. At that exact time, the height of the pyramid would become equal to its shadow plus half the base. In such cases, all angles other than 90 degrees in a triangle are equal to 45 degrees. In other words, both of these triangles are isosceles triangles. And obviously, this method was far easier than the previous one. Now, before we move forward, let me ask you, what would be the scale factor in this particular situation? This is how Thales might have managed to find the height of the Great Pyramid of Giza, which was around 481 feet at that time. So far, the discussion was revolving around the ratio of corresponding sides of similar triangles, which was equivalent to the study of scale factor. And the relationship established for the triangles only involved their sides, not angles. But there is another way of looking at the same thing. Suppose in right triangles ABC and PQR, one more pair of angles is equal. So we know in triangle ABC and PQR, angle ABC and angle PQR are 90 degrees each. And according to our consideration, angle CAB and RPQ are also equal. So triangle ABC and PQR are similar triangles. Criteria we have used here is AA rule of similarity. We know for similar triangles, ratio of corresponding sides are equal to each other. So we will look at pairwise equal ratios. First, let's pick these two ratios. So CB upon RQ equals BA upon QP. After some rearrangements, I can write CB upon BA equals RQ upon QP. Now please pay attention here, because here we are going to introduce the concept of trigonometry. What does this equation tells us? Two ratios are equal to each other, right? Yes. But what are these ratios themselves? Let's look at them one by one. For angle A in triangle ABC, CB is perpendicular, or you can say height, and BA is the base or leg. Correspondingly, for angle P in triangle PQR, RQ is the perpendicular and QP is the base. So equation is actually telling us that the ratio of perpendicular to base for angle A is equal to ratio of perpendicular to base for angle P. Or you can say that for two equal angles in two right triangles, ratio of their respective perpendiculars to their respective bases are equal. Values of these ratios are only dependent on the values of the angles and not on the size or side lengths of the right triangle. Now let's pick these two ratios. CB upon RQ equals CA upon RP. After some rearrangements, CB upon CA equals RQ upon RP. For angle A in triangle ABC, CB is perpendicular, and for angle P in triangle PQR, RQ is the perpendicular. And CA and RP are respective hypotenuses for angle A and angle P. So this equation is actually telling us that the ratio of perpendicular to hypotenuse for angle A is equal to ratio of perpendicular to hypotenuse for angle P. Finally, let's pick these two ratios. We are going to do the same things, and after that, for angle AA and angle P, BA and QP are the bases respectively, and CA and RP are the hypotenuses respectively. So this equation is actually telling us that the ratio of base to hypotenuse for angle A is equal to the ratio of base to hypotenuse for angle P. Now remember, angle A and angle P are equal to each other. Now before we move ahead, can you guess how many ratios are there for angle A? Here's a small hint for you. These are the ratios that we have just discussed, and if we do the reciprocals, we will get 3 new unique ratios. So now we have 6 equations. Now the answer to this question is the left hand side of all these 6 equations. CB upon CA, this one is the ratio of perpendicular to hypotenuse, which is known as sine of angle A, or simply called as sine A. BA upon CA, which is the ratio of base to hypotenuse for angle A, is called cosine of angle A, or simply called as cos A. The ratio of CB to BA is actually the ratio of perpendicular to base for angle A, which is called tangent of angle A, or simply called as tan A. Now tan A is also equal to sin A upon cos A. How? I'm going to leave this exercise for you guys. Now the ratio of CA to CB is the ratio of hypotenuse to perpendicular for angle A, which is called cosecant of angle A, or simply called as cosec A. Now you know that CA upon CB is reciprocal of CB upon CA, and CB upon CA is sin A, so cosec A is equal to 1 upon sin A. Similarly, CA upon BA, which is the ratio of hypotenuse to base for angle A, is called as secant of angle A, or simply called as sec A. This is the reciprocal of cos A, so sec A is equal to 1 upon cos A. And finally, we have BA upon CB, which is the ratio of base to perpendicular, which is called as cotangent of angle A, or simply called as cot A. Now cot A is equal to cos A upon sin A. So these two relations are also self-explanatory. Cot A is equal to 1 upon tan A, and tan A is equal to 1 upon cot A. The restriction on the values of angle A are going to be discussed in part 4. So these sin, cos, tan, cosec, sec and cot of angle A are called as trigonometric ratios for angle A. Correspondingly, we have these 6 ratios for angle P as well. Make sure to pause the video and go through all these ratios yourself. These sin, cos, tan, sec, cosec and cot of angle P are called trigonometric ratios for angle P. Values of trigonometric ratios for two equal angles will be equal, irrespective of the size of triangles they are a part of. So from time to time in history, the need for such values of ratios for specific angles started to gain demand, and people started making a list of such ratios. Although trigonometric ratios are not limited to acute angles, our discussion is only limited to acute angles. By the way, if you are still with us, it means you're liking what you're watching and probably want to watch more. So if you don't want to miss out any future videos, make sure to go to Inquisitive Thinking, click on the red subscribe button, and after that click on the bell icon and click on all, so that you don't miss any future videos and content. Alright, now suppose just like Thales you want to find out the height of a building, but unlike 600 BCE, you now have access to modern day measuring devices, one of which is an inclinometer. Now an inclinometer is a device which is used to measure angle of elevation or angle of depression of an object with respect to gravity, that is downward direction. Along with this, you now have sine, cos and tan tables for every integral values of angles between 0 degree and 90 degrees. A sine table contains sine values of some specific angles, and same goes for cos and tan tables. This is what sine, cos and tan table look like. We have integral values of angles from 0 degree to 90 degrees and their corresponding sine, cos and tan values. So now suppose you are holding an inclinometer at an eye level of A units from the ground. H is the height of the building, which is unknown here, and theta is the angle of elevation of the top of the building measured by the inclinometer. Distance DC is the known distance between your foot and the base of the building. So using basic geometry we can mark these lengths as well. Alright, first let's establish the known and unknown quantities. Known quantities here are your own height, that is A units, distance between you and building, that is B units, and angle of elevation, that is theta. The only unknown quantity here is height of the building, that is represented by H. First let us divide the given figure into two figures like this. Now we have a right triangle AOB and a rectangle OBCD. Now in triangle ABO, for angle theta, we will use the trigonometric ratio of tan. If you were thinking why, we'll see it in a moment. Now tan theta is equal to perpendicular upon base. Perpendicular with respect to theta and base with respect to theta. So perpendicular for theta is AB and base for theta is OB. So tan theta can be written as H minus A upon B. Here values of A, B and theta will be known, and the value of tan theta can be found in a tan table. So from the above equation, the value of H can be calculated, since there is only one unknown quantity in this equation. Now suppose you are 1.5 meters tall and holding inclinometer at eye level, and distance between your foot and base of the building is 50 meters, and angle of elevation is 65 degrees, which you have measured by inclinometer. So tan theta is equal to perpendicular upon base. Here perpendicular is again AB and base is OB. So AB is equal to h minus 1.5 and OB is equal to 50. The value of tan 65 can be found in the tan table, which is approximately equal to 2.1445. Now let's substitute this value, and from here we can find the value of h, that is approximately equal to 108.725 meters. So by using trigonometry we were able to find the height of the building without actually having to measure it, which came out approximately around 108.725 meters. Okay, now it's time to reason why we are looking specifically at right triangles, even though trigonometry is not limited to right triangles only. It's basically just for our convenience to find the length of unknown sides when sufficient angles and side lengths are given. You have already seen that only one angle and one side length is enough to find the other sides in a right triangle. Let's justify this argument. In triangle ABC, angle A is unknown, angle B is 35 degrees and angle C is equal to 59 degrees, and CA is equal to 4 units. The rest of the sides are unknown. So using angle sum property of triangle, angle A will come out to be equal to 86 degrees. Alright, now we are going to divide this triangle into two right triangles by constructing an altitude from A to point D on side BC. Now triangle ACB is divided into two right triangles, which are ACD and ABD. So let us separate out these triangles and we will look at them one by one. Here CD plus DB is equal to side CB. So let's look at this triangle first. In triangle ACD, AC is equal to 4 units, angle C is equal to 59 degrees and angle D is 90 degrees. So for angle C we will use the trigonometric ratio of sine. So sine C is equal to the ratio of perpendicular to hypotenuse, AD upon AC. AD here is unknown, whereas AC is equal to 4 units. Sine C is equal to sine 59. And using sine table, sine 59 comes approximately equal to 0.85. So 0.85 is equal to AD upon 4. From here, AD comes out to be equal to 3.42 units. What about CD? For CD, we will use the trigonometric ratio of cos for angle C. So cos 59 is equal to the ratio of base to hypotenuse. Base is CD and hypotenuse is AC. So CD upon AC is equal to CD upon 4 after substituting the value of AC. Using cos table, cos 59 comes approximately equal to 0.51. So CD is equal to 2.04 units. So using trigonometry we have found all the unknown sides of triangle ACD. Now let's look at triangle ABD. Angle B is equal to 35 degrees, angle D is equal to 90 degrees, side AD is equal to 3.42 units. The only sides remaining are AB and DB. Here is a small hint for you. Use sin B for side AB and tan B to evaluate side DB. So the values of AB and DB are approximately 5.96 and 4.85 units respectively. So roughly the dimensions of this triangle are 4 units, 5.96 units and 6.89 units. If we oversimplify these values, I can write AB equals 6 units, CB equals 7 units and AC was given, which was equal to 4 units. So this is why we are studying trigonometry in right triangles, just for our sake of convenience. Now given triangle was an acute angle triangle, what about an obtuse angle triangle? You can do the same things in a case of an obtuse angle triangle. So you have seen the importance of keeping a list of T ratios for different angles. Even though it's not necessary and not even practical to learn all of these ratios, values or sum of the ratios for specific angles can be calculated using simple geometry and can then be memorized. This task will be accomplished in next part of this series. So guys, this sums up part 3. Just in case you are facing any doubt or facing any problem, make sure to put it down in the comment section and I'll get back to you as soon as possible. If you liked this video, make sure to give it a thumbs up and subscribe to Inquisitive Thinking for more content. Stay safe, stay healthy and most importantly, stay inquisitive. We'll meet in part 4.